We've met the neuron and all the machinery to train it. Now we finally assemble those neurons into the first real neural network, the Multilayer Perceptron or MLP. It's the blueprint that every deep architecture is built from. Understand this, and CNNs, transformers, and the rest are just variations on the theme. Start with what we know. A neuron takes inputs, multiplies each by a weight, adds them up, adds a bias, and passes the result through a nonlinear activation. Inputs in, one number out. On its own, it can only draw a single boundary, but neurons were never meant to work alone. Put several neurons side by side, all reading the same inputs, each with its own weights. That's a layer. Where one neuron detects one pattern, a layer detects many at once. One might fire for edges, another for color, another for texture. A layer turns a single input vector into a whole vector of learned features. Now stack layers in sequence. The first is the input, the last produces the output, and the layers in between are the hidden layers, the heart of the network. Each hidden layer takes the features from the layer before and combines them into richer ones. Input, hidden, output, that's the multilayer perceptron. Making a prediction is just a forward pass. The input vector flows into the first layer, which produces a new vector, which flows into the next and the next, until the final layer emits the answer. At each step, it's the same operation we've seen all series. Multiply by a weight matrix, add a bias, apply an activation, repeat. Why the hidden layers? Because they let the network build features on top of features. The first hidden layer learns simple patterns from the raw input. The next combines those into more complex ones. Layer by layer, the network composes simple ideas into sophisticated ones, which is exactly what makes it powerful. This stacking creates a hierarchy. In a network that sees images, early layers might detect edges, middle layers, shapes and parts, deep layers, whole objects. Nobody programs this. The network discovers the hierarchy on its own, from data through training. Depth is what lets abstraction emerge. And here's the astonishing theoretical result. The universal approximation theorem says that an MLP with enough neurons can approximate virtually any function to any accuracy. Any pattern, any mapping from input to output, a big enough network can represent it. That's the mathematical promise underneath all of deep learning. But enough neurons can be arranged two ways. Width is how many neurons per layer. Depth is how many layers. In theory, a single wide layer suffices, but in practice, deep networks learn far more efficiently, reusing features across layers instead of memorizing everything in one. That's the whole reason it's called deep learning. In an MLP, every neuron connects to every neuron in the next layer. It's fully connected or dense. That's maximally flexible, no assumptions about structure. Every input can influence every output. It's the most general layer there is. And that generality is both its great strength and soon its weakness. The MLP is the foundation of everything that follows. A convolutional network is an MLP that shares weights to handle images. A transformer is layers of attention with MLPs inside. Strip any modern architecture down, and you find dense layers doing the final reasoning. Every specialization starts here. But the plain MLP has a hard limit. Feed it an image, and you must flatten the pixels into one long vector. A megapixel image becomes a million inputs, and fully connecting that needs billions of weights. Worse, it throws away the fact that nearby pixels belong together. It doesn't scale and it ignores structure. That problem is exactly what the next architectures fix. So that's the MLP, stack layers of neurons, pass data forward, and let depth build a hierarchy of features powerful enough to approximate almost anything. It's the original neural network and the core of everyone since. But to handle images without drowning in weights, we need a smarter structure, one built for vision. Next time, convolutional networks. See you there.